Thanks a lot for the invite to talk at this workshop, which I think discusses very important upcoming challenges. We hope that the methods on learning to anticipate that myself and some excellent students at UIUC are working on can help tackle some of those challenges. I call those students the magicians. They are really the ones that deserve all the credit of the work that I'm going to show. They are the ones which make things work. I'm sure it is no surprise to all of you when I say that computer vision and machine learning has been remarkably successful in the last couple of years. I'd argue that models which analyze data work very well by now, and we're able to achieve impressive results for image classification, object detection, semantic video segmentation, and human pose estimation. So are we done? Obviously not. What we care about is to personalize our life. Some people refer to it as automate, but I think personalize is more adequate. In order to personalize, we really need algorithms that don't only analyze, but rather anticipate. What do I mean by that? Consider the example shown on this slide, where two kids hassle each other chasing a ball. Humans driving by in vehicles would be quite cautious, wondering whether the kids step aside and yield to oncoming traffic, or whether the kids run into the middle of the road without checking. We wonder about it using mental simulation to imagine possible future scenarios, some of which have extremely unfavorable outcomes. I don't think at this point we have systems that are able to imagine complex future scenarios, like the one illustrated on this slide. How do we get there? To get there, I think we need to combine the vision of David Marr, a neuroscientist that computer vision researchers are very familiar with, and the vision of neuroscientists like Rodolfo Linas and Kenneth Craig, who argued that a creature must anticipate outcomes of movements to navigate safely. To achieve this goal, we connect a variety of research topics in the fields of semantic segmentation, modeling of probability distributions, learning of vision and vision plus language models, as well as autonomous agents. In the remainder of this talk, I want to focus on two research projects that I think could be particularly relevant in the agriculture context. Specifically, I want to tell you about two works. First, how to explicitly infer relations between moving objects. This work will also be presented by Colin in the main conference at this year's CVPR. Second, how to address challenges for object detectors when working with weakly annotated data. This work will be presented by Jason and collaborators in the main conference at this year's CVPR as well. Alright, let me tell you about dynamic neural relational inference. We are interested in modeling the movement of entities, such as body joints or athletes in an arena. Their motion is influenced by the unseen interactions or relations they have with each other. Knowing how different entities interact with each other can improve the ability to predict their future states. Furthermore, it is reasonable to expect the types of interactions to change over time. For this, we introduce dynamic neural relational inference, or dNRI for short. It explicitly models the interactions between different entities. Relations Z are modeled as discrete latent variables which are inferred from the observed trajectories of object representations X. Unlike prior work, we want the relation C to change over time. Here's an overview of how dNRI works. Given an input trajectory, we want to predict a distribution over relation types at every time step. During training, this is done using an encoder, which utilizes information from both the past and the future of the sequence to estimate the relation distribution. After predicting these distributions, they are used by the decoder to reconstruct the input trajectory, except shifted forward one point in time, so that we can use the model during inference to predict the future of a sequence. We additionally train a sequential prior distribution over relation types, which is solely a function of the past. We train dNRI using the evidence lower bound, which takes the following form. The first term is a reconstruction loss. It is used to train the decoder to make correct predictions for the future time steps. The second term is a carrier divergence between the encoder and the prior. This encourages the encoder, which sees both the past and the future of a sequence, to resemble the prior, which only sees the past of a sequence. The prior distribution factorizes in an autoregressive manner and is modeled in the following way. At every time step, the input features for all entities are passed through a fully connected graph neural network. This results in a feature representation for all directed pairs of variables, represented by the edges of a graph. These embeddings are passed through a forward LSTM in order to accumulate information about the history of the sequence. Finally, at every point in time, the hidden state of the LSTM is passed through a multi-layer perceptron producing the logits of prior distribution. As mentioned previously, the encoder considers both the past and the future of the sequence to produce relation distributions. More specifically, it uses the same feature representation for all pairs of variables that were computed by the prior model. It then passes these through a backward LSTM to accumulate information about the future of the sequence. The hidden states of the backward LSTM are then concatenated with the hidden states of the forward LSTM produced by the prior model and are passed through a multi-layer perceptron to produce the logits of the encoder distribution. Next, we must sample relation variables. To ensure end-to-end trainability of the model, we want to differentiate through the sampling process. Since sampling from a categorical distribution is not differentiable, we instead sample from the concrete distribution, which is a continuous approximation to the discrete categorical distribution. Given distribution logits H, this process proceeds by first sampling a vector G from the standard Gumbel distribution and then computing the following update, where tau is a temperature parameter. During training, the logits are taken from the encoder distribution. During inference, the logits are taken from the distribution. The decoder processes the input features at a given point in time by passing them through a graph neural network. For this model, there is one set of edge functions for every relation type, and the function used for every pair of variables is determined by the relation variables that were sampled in the previous step. The hidden state for each entity is then passed through a linear layer to produce a distribution over its states for the next time step, conditioned on the past. The final decoder distribution is autoregressive and consists of the product of these individual distributions. To recap, given a set of input trajectories, dNRI first passes them through the encoder and the prior to produce distributions over the relations between each pair of entities at every point in time. Relation variables are sampled from the appropriate distribution, which are then used by the decoder to select the appropriate graph neural network parameters for each pair of entities, which are then used to predict their future states. Our model extends neural relational inference by Kipf and others from ICML 2018, hereafter referred to as static neural relational inference. This model produces one set of relation variables, which are then used at every point in time by the decoder. dNRI, on the other hand, produces a separate distribution over variables at every point in time, which allows to increase modeling flexibility when relations between variables are expected to change over time. Additionally, static NRI uses a fixed uniform prior over relation types, while dNRI uses a sequential prior, which is learned from the data. I will now present experimental results which cover several data domains. For each set of experiments, we compare dNRI against the following baselines. We train a static NRI model and evaluate two ways. The first approach predicts relations using the provided input and uses these for every step of forecasting. The second approach re-evaluates the relation predictions using the most recent predictions during every step of forecasting. Additionally, we train an LSTM, which predicts the trajectory of each entity independently, an LSTM which predicts all trajectories jointly, and a graph neural network model that is equivalent to the dNRI decoder, except it uses one set of parameters and a fully connected graph. We first ran experiments on a synthetic physics simulation dataset we created with the purpose of analyzing dNRI's ability to recover ground truth dynamic relations. Each trajectory in the dataset consists of 3 particles. The first 2, in red, move with some constant velocity. The third, in blue, is initialized with a constant velocity, but is additionally pushed by the other particles whenever their distance is smaller than a threshold. We trained a static NRI model and a dNRI model on this data. Static NRI, which cannot properly model the dynamic relation changes, has an average relation prediction F1 of 27.1, while dNRI has an average relation F1 of 54.3. Higher is better. The second dataset consists of motion capture recordings taken from the CMU motion capture database. We use 2 different subjects. The first contains trials where the subject is walking. The second consists of trials where the subject stands stationary for a different amount of time and then jumps forward. Here are the results and a sample visualization for the walking subject. the dNRI model is able to predict many frames into the future without straying too far from the ground truth skeleton. In contrast, the static NRI model makes significant errors. We visualize some relations predicted by dNRI, which shows that relative to the heel of the skeleton, different relation types are active when picking it up, moving it forward, and putting it back down. Here's a comparison between dNRI and static NRI for a walking subject. Here are results and visualizations for the jumping subject. Once again, dNRI's predictions are more closely matched by the ground truth skeleton compared to the static approach. The visualized relations for dNRI indicate that different relations are used when the subject is preparing to jump than when the subject is in the middle of the jump. Static NRI is unable to properly model different phases of motion like this. Next, we study basketball trajectory data. Each trajectory consists of the 2D positions and velocities of the offensive team, consisting of 5 players. These are processed into 49 frames, representing approximately 8 seconds of play. When computing metrics, 30 frames are provided to the model, and the remaining 19 are predicted. For visualization purposes, we feed 40 steps to the models and forecast the remaining 9 steps. We show the prediction errors and a sample trajectory. The static model mispredicts the general path of the red and blue players, while dNRI is able to capture the correct movement direction. Visualizations of predicted relations by both models are shown on this slide. We can see that dNRI initially predicts an interaction between the orange player and both the blue and the red players, which is highlighted in pink. This interaction is not needed by the model later. Static NRI, however, does not predict this relation, which may explain why its performance is suboptimal in this case. Finally, we study the IND traffic dataset, which consists of recorded vehicles, bicycles, and pedestrian trajectories at different intersections. Unlike the other datasets studied in this work, the number of entities varies over time as they enter and leave the intersection. Consequently, the RNN models and static NRI, which assume a constant amount of entities at all points in time, cannot be used. For evaluation, we divide recordings into 50-step sequences. Whenever an entity appears in the sequence, its position is provided as ground truth for 5 steps, and the model is required to forecast its location for the remainder of the sequence. dNRI, which can model multiple types of interactions between different entities, outperforms the FC graph baseline here. Let me now shift focus and talk about weakly supervised object detection. This is joint work with Jason and an amazing set of collaborators at NVIDIA and UC Davis. Thanks to everyone for all your support. We aim to train detection models with weak supervision, which comes in only the form of image-level class labels. Existing solutions are promising, but suffer from 4 main issues. First, non-salient objects are often ignored. Second, multiple instances are often grouped together. Third, predictions are dominated by discriminative parts such as faces. Lastly, training of object detectors is often very memory demanding. To address the first 2 issues, we propose a new self-training algorithm which encourages diverse and accurate predictions. For part domination, we develop a learnable and structured spatial dropout. Lastly, we present an efficient backpropagation method to deal with the memory consumption of those object detectors. Because of time, I refer you to the paper for the details of those contributions. Let me show you instead some results. Those contributions that I just mentioned permit to achieve state-of-the-art results on established benchmarks like COCO and Pascal VOC. In addition, and thanks to the memory efficiency, we are also able to report the first weakly supervised video object detection results. As shown in the picture, our model detects multiple objects with great recall and accuracy. It differentiates instances of the same class and recovers accurate boxes. In summary, I think these contributions permit to train accurate object detectors from weakly labeled data, that is, from annotations which only come in the form of image-level tags. I think this is particularly useful in an agriculture context where annotations are sparse and often hard to come by. With that, I conclude my talk by thanking my funding sources and all the collaborators as well as you for listening. Feel free to reach out with any questions that you may have, which I'm very excited to answer. Thank you.